Very good. All right. So, today we're gonna continue. Oh, am I recording? Yes. Oh, I'm not recording. I am recording. Good. So, today we're gonna continue our conversation of loop diagrams in QED. If I can figure out how to use the pointer. Yeah, there we go. Loop diagrams in QED. And we discussed fermion self-energy. We're going to discuss fermion self-energy and vertex corrections. So the review of what we went through last two lectures actually, is that we discussed the vacuum polarization at one loop, which is the correction, the one loop correction to the propagator of photon in QED, right? So this is a propagator of photon. We said that it's inconvenient to package everything in terms of the one particle irreducible diagrams, the sum of one pi diagrams, right? That we denoted by pi mu nu of q. And then we said that because this is a gauge theory, it has the regulator of the theory should respect gauge invariance. And the regulator that we used was dimensional regularization. And the point of this whole calculation we did was to show that dimensional regularization indeed preserves gauge invariance. So how did we show that? Naively, if you were to just put a sharp cutoff in momentum without dimensional regularizing, we saw that there is a term that was growing like the cutoff squared, and then there was a log term. The term that was growing like cutoff squared was the one that was offensive to gauge invariance. And using dimensional regularization, we saw that that term just disappears, right? Along the way, well, okay, so what was dimensional regularization? We took our four integrals. Our four-dimensional, 2+1 dimensional momentum integrals, and wrote them as d+1 dimensional space-time integrals. But because we want to keep the dimensionality of the propagator the same, we had to introduce a new length scale, energy scale, and then took it to the appropriate power so that the whole thing maintains its dimensionality. This is the scale, renormalization scale. This energy scale is the renormalization scale that we talked about. We use a bunch of tricks. The tricks that we used, the two important ones was Feynman parameters and Wick rotation. Both of these two tricks are going to be repeated over and over again in all the one loop and higher loop diagrams. So we're going to go through two more one loop diagrams in QED in the remainder of this course, and we're going to see different versions of Feynman parameters, these integrals, and Wick rotation is always also there to make the integral converge well-defined. So the Wick rotation was just sending L0, the zero component of momentum, to IL Euclidean. All right. So after using Feynman parameters and Wick rotation, we wrote the 1pi, this guy, the 1pi propagator, right? Which was the we called it vacuum polarization at one loop, in the following form: minus 4i e squared, E is the electric charge, V of d+1, this is dimensional regularized, right? Integral over x of 0 to 1, this x is the Feynman parameter x, right? Delta of q squared over mu squared to the power of w minus 1. Hopefully you guys remember what these parameters were. W is d minus 1 over 2, right? It's just a dimension. This whole thing is multiplied by these two terms. This is the log divergent term, and this was the offensive term, which was growing like lambda squared, the cutoff squared. And then we saw under the analytic continuation that this term, the most divergent term that violated gauge invariance in dimensional regularization, goes away. The coefficient is 0. This drops, and this is our final answer, right? So now we made two comments about this final answer. First is that it's transverse as required by gauge invariance. Transverse means that it's proportional to this p mu nu, P mu nu, if you recall, is the projection to the directions perpendicular to the forward momentum, right? Because it's a massless vector field, and it can only have degrees of freedom in the subspace perpendicular to its for momentum. Then the other comment we made was that it's log divergent. Therefore, it's convenient to work with in 4 minus epsilon dimensions, 3 plus 1 minus epsilon dimensions, and expand this small epsilon, right? So we saw that we took this pi mu nu q. We said that its form is fixed by Lorentz invariance, basically. And then there's a piece that's a Lorentz scalar, pi q squared, which we were to interpret as renormalization of charge, right? Electric charge. It was, we did this expression was minus 8 over 4 pi integral d over x minus 1 minus x. These are Feynman parameters. In the 4 minus epsilon expansion, the coefficient that sits here is 2 over epsilon plus ln of 4 pi e to minus gamma. Gamma is that coefficient. I forget what it's called. It's a constant, right? It's a famous constant, mu squared over del squared. So here one comment is that because this is a constant that appears always through the expansion of the log, we could also package this here and work with ln of mu squared over delta. You'll see in a bit that I'll do that. That has a famous that has a name, and we'll do that very soon, right? We defined Baire parameters, right? These Baire parameters are the parameters in the Lagrangian, right? And the alpha, which is the coupling constant, is just e squared over 4 pi, right? The potential is just alpha over r. All right. So if we take this coupling, we notice that the charge renormalization is scale dependent. So alpha of q squared renormalized as scale q is like alpha of 0 renormalized as 0 energy multiplied by this expression, right? This was due to the fact that in vacuum polarization, the coefficient the correction that we're getting, the one loop correction we're getting, was not adding a mass. It was not a renormalization of the mass, but it was just an overall factor sitting in front of 1 over q squared, right? So we said that's a renormalization of charge. So if there's this correction is small, you can view it that you could bring this down here and work with pi of q squared minus pi of 0. We defined that to be pi hat. We calculated it, and we found this final expression, minus 2 alpha over 4 pi. Remember that this is perturbation theory in alpha, right? So this is the first order correction. So these are Feynman parameters, ln of m squared over m squared minus x, 1 minus x q squared. This was coming from this delta. We said that when the denominator of log goes negative, there's a branch cut. Above and below the cut, the imaginary part of pi, we evaluated it, and we saw that it has the same Q dependence as the cross-section at tree level. So this was a one loop calculation. We saw that this has the same form as a cross-section at tree level. And then we mentioned that it's not a coincidence. It's actually a theorem for the 2-to-2 scattering. It's called optical theorem, but for the 2-to-2 scattering, the form of it is like this. The imaginary part of the amplitude of K1, K2 going to K1, K2 is related to the total scattering cross-section from K1, K2 to anything, right? And diagrammatically can view it this way. So the one loop K1, K2 going to K1, K2 is like this, right? We're looking at the imaginary part of it, and roughly speaking, you can think of this as being cut into half, and there are two pieces, and this is what this expression is. Yeah, but this is just schematic. Just these are their pictures to remember this rule, right? The rule was that the imaginary part of the amplitude for when the initial and final states have the same momenta is at one loop is related to the tree level results squared, the cross section. All right. We also said that at the end of the last lecture, in the non-relativistic limit where Q naught energy is much smaller than mass, the T matrix was like S matrix was 1 plus IT, right? So T matrix captures the interaction part of the S matrix, is related to the potential felt by charges. In particular, P prime ITP is the potential, and the factor that sits in front is just conservation of momentum for momentum. So the one loop correction to the potential takes the following form. So this is the standard potential, electromagnetic potential. Recall that alpha is E squared over 4 pi. So this is just a Coulomb potential. And the correction to it is order alpha, right? And it takes the following form. Now, the effect of this correction, this one loop correction, this is a quantum correction, right? Is screening, which means that if these two charges were just pure charges, they would be repelling each other through this interaction. But these charges are, in a sense, screened by a cloud of fermion, anti-fermion pairs that are being created here. And they also feel there's an effective interaction that this whole thing feels, and that is described in the following way, right? And then we said that in a sense, due to the presence of these corrections, the vacuum of QED is like a dielectric medium. All right, any questions about this part? I'm just reviewing the discussions from the last lecture. All right, then, so that was our discussion of the vacuum polarization. There are two other diagrams in QED that we have to look at. One is the fermion self-energy, which is a propagation of the fermion, because QED, recall, is just a theory where you have a U1 gauge field, a photon, coupled to a fermion, right? A Dirac fermion. So there's the propagator for the fermion, there's a propagator for the photon, and then there's a vertex, because they interact, right? Those are the three diagrams that we have, and those are the three that we have to deal with. So far, we've only discussed this one. So today and on Thursday, we're going to discuss these two. Today, we're going to discuss this and start the discussion of vertex correction. So I was planning originally in finishing the vertex correction today, but I realized that I won't do justice to the infrared divergences if I want to rush it. So we're going to discuss this in detail in the next lecture, because IR divergences in quantum field theory is a deep topic, and parts of it is still like research and it's being developed these days, parts of the story. So it's not a cleanly sorted out story, fully sorted out story yet. All right, so now this was vacuum polarization. This diagram is called fermion self-energy for obvious reasons, right? So that's what we're going to look at. All right, so fermion self-energy, of course, you could use this one particle irreducible diagrams and write it as 1 pi plus 1 pi, 1 pi, blah, blah, blah. And then there's a resummation. There's a formal resummation in the following form. So this is the free propagator. This is the free bare mass, right? I over P slash minus M is the propagator, if you recall, in the Gaussian theory. Then this guy is the free propagator 1 pi, which I'm representing this way, the free propagator. Now, the important thing to remember is that now, because we're dealing with fermions, this guy is actually a matrix. It's a 4x4 matrix, right? Because the propagator, these guys, P slash was P mu gamma mu. So these are also matrices, right? So when I write M, I mean M times identity and the 4x4 representation. So these are all matrix multiplications, right? Always keep that in mind. Then this is I over P slash minus M sigma P. This is the 1 point amputated, 1 pi amputated 2-point function. Good. Any questions about this part? All right. So I just said this. Sigma P is a matrix with spin indices. Now, sigma P is supposed to, what we're calculating is one loop, right? So we're looking at order alpha corrections, right? So there will be an order alpha corrections to P slash and order alpha corrections to M, right? So it's convenient to just write it in the following form, right? So you view it as by you can repackage this as a renormalization of mass and a renormalization of an overall constant Z2 that sits here, right? So this guy is like some sort of a wave function normalization, right? These sides are multiplied by something. Well, we're gonna discuss this in more detail. So after this renormalization of mass, so there will be a true pole for the propagator that will be the physical mass of the fermion, right? And this guy is the residue of it, right? So we're going to read off the residue, and that residue is going to be the controlling the normalized wave function normalization. This is at one loop, the 1pi 2-point function is the following diagram. So the fermion is propagating, it emits a photon and it comes back, right? So this is a diagram we're going to look at. This is the only diagram at one loop. Any questions? All right. So let's put some labels. Q is the external momentum. K is the internal momentum. Of course, we have to integrate over K. So what does it look like? For simplicity, again, we always write the amputated thing. So what we're going to deal with, we're going to integrate over K, the internal thing, right? But I'm going to instantly dimensional regulate it. So the integrals are in d+1 dimension. I've introduced a mu parameter in 4 minus d+1 to keep the propagator, the whole thing dimension, keep the dimension of the whole thing fixed. I have two vertices. Here are the contribution of the two vertices, minus IE squared, gamma mu, gamma nu, right? These are the two vertices. If you recall, each vertex was minus IE gamma mu, right? I have this fermion propagator, ISF, sorry, U minus K. ISF Q minus K, and then this is a photon propagator in this form. I've written this down in Lorentz gauge. Today we're going to see that there's another gauge that's very convenient, which basically the effect of which is called the arc zeta or arc C, R zeta. Yeah, arc C gauge. The effect of which is to put C minus 1 here. Actually, plus C minus 1 here. So the C equals 0 corresponds to the Lorentz gauge, but this is a more general gauge. It's called arc C, but I'll describe a little bit more. I'll describe this a little bit more later. All right, so this is the integral we have to do. Are there any questions about the form of the integral? So far, it's just Legos. Okay, very good. So let's focus on the integrand, right? So the integrand, let's just write down what these guys are. It's always easier to write these I over P slash minus M. You just complete the score downstairs and write this as I times P slash plus M over P squared minus M squared, right? So that's what I'm doing here. So I have I over K squared, right? So here's my one factor of K squared. The other factor of K squared comes from here, right? So I've just taken it out. So there's K squared squared. This is this propagator, K minus Q squared minus M squared. This is that extra bit because the fermion propagator was 1 over Q slash K slash minus Q slash plus M squared, right? And then this is just the extra bit here. Good. So let's focus on this term and do some simplifications here, right? So you could write this as two terms. The first term has this K squared in it, right? It has this K squared in it. And eta mu nu just leads to contraction of these indices. So it's K squared gamma mu, this expression. The second term is minus here, right? So K slash K slash, right? K minus Q slash Q slash minus K slash plus M, right? So these are the two terms we're dealing with. The important point is this. Let's split this into two terms. The first term has this K squared in it. One factor of K squared and one factor here, they cancel out, right? So this is the term that I'm going to call term number one. And then the second term is this term. They just use the algebras. I will not, you guys I trust you guys can reproduce these. But so this is the first term, and then this is the second term. I'm calling term one, term two. We're going to discuss them separately for reasons that you're going to see, because the physics of them is a little bit different. All right. So let's focus on term number one. So term number one is the following expression. I have 1 over K squared, 1 over K minus Q squared minus M squared. Because this is like 1 over AB, right? 1 over K squared, 1 minus Q minus K minus Q squared minus M squared. I can do Feynman parameters. So I do the Feynman parameters. This is the integral I end up with, where delta x is defined the way that we normally defined it, previously defined it, right? You guys remember Feynman parameters trick? It's something that we're going to be using over and over again, a million different versions of. So it's a very useful trick. All right. So we first did so far we've only done the Feynman parameters. The second step is this change of variables. This change of variables we also do all the time. It's a very typical change of variable. We did this for the vacuum polarization as well. So we introduced this L mu vector. After this change of variables, our integral takes the following form: I e squared mu 4 minus d plus 1 integral of d of x integral of L. Actually, I've also done Wick rotation. I've done not yet. Actually, I've not done it yet. The term that I'm dealing with takes the following form, right? So this is L squared minus delta squared. That's the part that I'm interested in, right? Then we do Wick rotation to be able to write down the integral and to evaluate the integral. Comes out of it these gamma functions, right? So if you recall, when we did the Wick rotation, these gamma functions were appearing canonically, and this is the expression we're dealing with. I've also, because I'm in Euclidean space, I can write down the integral in polar coordinates. That's what I've done, right? So again, I trust you guys can follow these steps through. Then we could notice that we've actually switched the exact same method with what we use for polarization of the photon. We changed the order of the L integral and the X integral in the Feynman parameters. So we changed the order, and then we could evaluate this integral, right, analytically. And the result is, our final result is minus alpha over 4 pi and integral over x of this expression. This is term number one, right? The part to pay attention to is this, right? This is where the physics, well, an important part of the physics is here. Are these steps clear? Maybe it's a little bit quick, but so what we did was that we just wrote down the one loop correction to the Fermion propagator, and we used our Feynman. So we split it into two terms. For the first term, we could use this simple Feynman parameters. Well, that was like 1 over AB, right? Then we did this change of variables that we did the exact same thing last time. We did the exact same Wick rotation as last time, and this is what we evaluated at the end, right? We changed the order of the integrals. Now, turns out that, well, I think I leave it to you guys to discover this, but turns out that this guy has a log divergence. You could do dimension counting and find that. So it's natural to expand it in 4 minus epsilon dimensions, right? So when you expand this in 4 minus epsilon dimension, you just, as we did before, you're going to end up with minus alpha over 2 pi integral over d of x there is the divergent piece, which is 2 over epsilon multiplied by this bit, right? Plus log of 4 pi e2 minus gamma mu square over delta. So this form should look very familiar. This form should look very familiar from the last calculation, right? So I said that just a few slides ago, I said that this 4 pi e minus gamma appears in all these calculations, and I can actually push it into epsilon. We will see that in a second. So this term is the divergent term that we found in 4 minus epsilon expansion in dimensional regularization. Discarding this term is called minimal subtraction. It's a regularization scheme. It's often called MS scheme. MS as in minimal subtraction, right? Just discard this term. There is another thing that's called MS bar subtraction, which is discard this term and this 4 pi e log of 4 pi e2 minus gamma. MS bar subtraction is more commonly used in quantum field theory. Just telling you guys what is a simple thing what's the thing that you see every time you open a quantum field theory book. All right, so this is the result of the first term. Now let's do the calculation for the second term. So we want to calculate the contribution of the second term to the propagator. We still have this minus I squared mu integral over k parameter, right? Now here we have 1 over k squared, right? 1 over k minus q squared minus m squared, and this is the numerator. To repeat what we just did, we have to use a different Feynman parameter trick. Previously, what we had was 1 over k squared, 1 over this. So we use an expansion for 1 over ab. Here we have to use an expansion for 1 over a squared b. And this is the integral we use. This is called the Feynman parameter integral, right? So we use this integral and write this guy as an integral over x and y from 0 to 1, 2 times y, this Dirac delta function, divided by k minus xq squared minus del of x cubed. I leave it to you guys to convince yourself this integral is this identity is a sensible identity. Plugging this back into the expression for the contribution of the second term to the propagator, we find this expression. So we have, no, this is good, actually. No, I'm not missing your coefficient. Minus 2i squared mu integral over d of x, 1 minus x. I've done the integral over y because there was a Dirac delta function. That was pretty easy, right? And this is the expression we find. Notice that we're dealing with the Feynman parameters with 3 factors in the denominator, 1 over a squared over b, and that's why I have this k minus qx squared minus delta cube. You instantly see that as before, we define this as L vector so that the denominator is just L minus delta cube. We did that before as well. So our next step is pretty clear. We do this change of variable and Wick rotation. Now, if you recall, we also introduced, this variable delta over L2 plus delta to just simplify our math, our notation. And with that, actually, yeah, am I using this z parameter here? Yeah, I'm not using it, so never mind. I'm not using the z parameter at all. So minus alpha over 4 pi gamma of epsilon over 2, this integral is the expression you find in a 4 minus epsilon expansion. Now, as before, you could look at the divergent part. The divergent term comes from here, right? This is the most divergent term. And in 4 minus epsilon dimension, its divergence is of the form alpha over 2 pi q slash minus m 1 over epsilon. That's the minimal subtraction scheme. And the MS bar scheme, you redefine 1 over epsilon by shifting it with 1 over 2 ln of 4 pi e to minus gamma. This is what I meant by saying that you could push this constant into epsilon, call that epsilon bar, and this is the ms bar scheme. Discarding this divergent term is the ms bar scheme. So putting the two terms together, what we find is that in dimensional regularization, near 4 dimension, in 4 minus epsilon dimensions, combining term 1 and 2, we get a total divergent term, which is, this is ms, which is alpha over 2 pi, 3m over epsilon bar. This is log divergence, right? So you learn that your sigma of q, the fermion self-energy, takes the following form, right? 3m alpha over 2 pi. This is just the scalar part of it. 1 over epsilon bar. This is the divergent piece, plus the alpha prime, plus the one loop correction, right? The first order correction. Let me pause here, right? So this is what this is. This is the correction to the propagator of the fermion, the scalar part of it, right? This is the divergence. It's log divergent. This is the log divergence in 4 minus epsilon dimension, and this is the one loop correction. You know it's one loop because it's proportional to alpha. Recall alpha was epsilon, was e squared. Each vertex contributes to e. To have a loop, you need two of those, right? Good. This is the expression we're going to try to interpret physically. So if there are questions, now is a good time to ask. So clearly scale dependent. This divergent piece is the divergent piece that we'll have to renormalize by to relate the bare parameters to the physical parameters. And this is about the running of the physical parameters. So if you look at the form of the propagator, is I over q slash minus m minus this sigma of q slash, right? The pole of the propagator, which is the 0 of the denominator, right, is the physical mass. So we would like to read off the physical mass, right? That's the 0 of the denominator of the propagator. So q slash minus m, this m is the bare mass, minus sigma of q slash on m pole has to become 0. All right, so let's massage this. This means that, so q slash is m pole is equal to bare mass plus sigma of m pole, right? Now in the ms bar scheme, so this guy is divergent. There is no way of, mathematically speaking, there's no way of splitting a divergent term into a divergent piece and a finite piece. However, that's the job of a regulator, right? A regulator does that for you. ms bar scheme that we just introduced, this dimensional regularization scheme we just introduced near 4 dimensions, 4 minus epsilon dimension, precisely does that for you. So it separates it into this sigma divergent m pole, which was, we said, 3 alpha over 2 pi m over epsilon bar, m pole over epsilon bar. This was the ms bar scheme. And the correction was this alpha over, I'm just reading from here, right? Alpha over 4 pi m pole 4 plus ln of mu squared over m pole squared, right? Good. Now take this term. Sorry, how do I want to say this actually? Yeah. Now what is m of ms bar? It's just m times 1 plus 3 alpha over 2 pi 1 over epsilon bar, right? The physical, so this was the bare parameter. This was the renormalized one. And this is the physical one at scale Q. Well, this is the physical one. That has the correction, alpha prime corrections. I have to solve this equation evaluating everything on the physical M pole. Now, M pole is like M regulated, MS bar, up to alpha prime corrections. Because I'm doing this expansion to the first order into alpha prime, I can replace M pole, everyone on the right-hand side with MMS bar at the cost of alpha prime. Sorry, I say alpha prime. And the cost of, I'm such a string theorist, alpha squared, at the cost of alpha squared corrections, right? Because we're at one loop, it doesn't matter, right? So what we solve is the equation that we solve is that M pole is the MMS bar 1 plus alpha over 4 pi, this expression, right? So this is the correction. This is the renormalization of mass due to interactions, right? Are we good? And clearly, this is the correction, alpha prime correction. This is small correction. All right, any questions about this? This was, I know that I'm walking you guys through a lot of algebra and analytic continuations, but that's just how field theory, perturbation theory, and QFT works. So are there any questions here? I will try to actually comment a little bit more about the physics of what we are doing. Dimensional regularization, view it at this point, you should view it as just like a trick to deal with these infinities and these divergences. But in part 2 of the course, we're going to actually systematically explain where do these come from, what is going on, right? There's a pretty deep story associated with these. Actually, before getting to do that, we have to introduce counter terms. There's a whole like machinery that's been developed, but eventually we're going to get to the mathematics of it as well and describe what's going on. All right. Any questions?
You said that there's no way to split a divergent term to a divergent term and a finite term. Could you elaborate more on that? Why is that?
If you have an expression that is divergent, right, formally divergent, there's no sensible way of saying this is the divergence of it and that's a finite piece, right? Because the divergent term is always defined up to a shift, up to a finite shift, right? There's no, I don't know how.
So you mean no non-trivial way?
There's no canonical way.
Oh yeah, okay.
There's no canonical way. It's arbitrary. It's arbitrary, right?
Yeah.
Yeah. So, all right. So this was about we said that up here, we said that we're after 2 parameters. Where was it? Here. We're after the physical mass that we found. The second thing that we're interested in is this Z2. This Z2 is the renormalization of the wave function. It's the residue of the pole we just found, right? So now we found the pole, and our next step is to find the residue. All right, so let's try to find the residue. So how do you find the residue? To find the residue, we need to expand the denominator near the pole. So we're going to have Q slash minus M pole, and we write it in this form, right? Plus higher order terms. The residue of the pole is simply this coefficient, the inverse of this coefficient, right? So if you know sigma, you know the pole and the residue, right? And it's just a matter of algebra to take derivatives with respect to Q slash and find the answer. I'm giving you the answer. It's minus alpha over 2 pi 1 over epsilon bar. But I want to make a comment here. You should be always a little bit up. I don't know if this was clear up to this point, But when I said that, when we were, sorry, let's go back to our discussion of divergent terms, right? When we're talking about the polarization of the vacuum polarization, there was a lambda squared divergence. This was offensive. It was like violating the gauge invariance. And then there was a log divergent term. The lambda squared divergent term likely got canceled in the realm of dimensional regularization. So it was all gauge invariant and good. There's a log divergent term. But the log divergent term itself could depend on the gauge. This is something somewhat subtle. It's somewhat subtle, but this is actually what's going on here as well. And if you pick a textbook on quantum field theory that uses a different gauge, you're going to find a different answer here for this divergent term. I'm going to comment on that again. Right? But hopefully in this prescription, you see everything we did up to here was just basically we wrote down the 1pi diagrams at one loop, right? We wrote the integrals. The set of techniques and tricks we used was Feynman parameters. We did redefine our integral variables. We did Wick rotation, right? Analytic continuation is what was sort of implied, right? So these were the tricks that we used. And then we expanded in 4 minus epsilon dimensions, right? And we talked about the MS bar scheme, which is minimal subtraction, which subtracts the coefficient of 1 over epsilon bar, right? Epsilon is this 4 minus epsilon. So that is the minimal subtraction. It should be, hopefully I've explained an algorithm to you guys that if I just give you some crazy diagram, you just use Feynman diagrams to write it as Legos. Next, you do dimension counting. If you find anything, well, it's a gauge theory, it's a QED diagram, so you should be doing dimensional regularization. That, I promise you, I haven't proven to you, but it's true. It guarantees that there won't be any divergences beyond log. That's good, right? Now, when you take the log divergences, you use Feynman tricks, you use analytic continuation, change of variables, all of that, those tricks. And then finally, 4 minus epsilon expansion. You look at the divergent term, you do the minimal MS bar subtraction, you obtain the running of your physical couplings. You obtain the renormalized 2-point function or whatever is the diagram that you have, right? If you take any limit of it, if you take a non-relativistic limit, you could recover, for example, as we saw, the correction to the Coulomb potential. Good. Is the algorithm, is the idea clear? Because we're doing a sample calculation in quantum field theory. All right. I said there are 3 diagrams in QED. We discussed 2 of them. Now let's discuss the third one. The third one is the vertex correction. And it's the one that has, on top of everything I told you so far, the UV divergences that we've been discussing. It has subtleties regarding infrared divergences. So this is going to be something that I was hoping to describe today, but I think it's physically important. So we're gonna postpone it to the next lecture. We're gonna set up the calculation of vertex correction, right? And then discuss the source of these infrared divergences in the next lecture. All right. So what are we talking about? We're talking about 1pi vertex correction at one loop. This is the only diagram that contributes at one loop. Right? Is that clear? So before the correction, the ordinary vertex was minus IE gamma mu. Gamma mu is a Lorentz vector. Just by Poincare invariance and everything we know, this guy, whatever the form of it is, this should also be a Lorentz vector, right? So I'm going to call this lambda mu. We're going to calculate the amplitude diagram using Legos, Fermion Legos. Of course, it will depend on K1 and K2. Now, K1 and K2 are no longer equal because you're radiating a photon. This is the source of these IR divergences because this photon could carry arbitrarily low momentum. Well, sorry, let me not. No, that's not. Let me not comment on those things yet. All right, so this is K1, K2. I have three vertices. So I have minus IEQ. I have three gamma matrices, gamma mu. Oops. I think I messed up. No, that's good. No, wait a second. This does not seem right. One of them is mu. Yeah. All right. Good. Because I have a mu index, it has to be here. So this is gamma mu, gamma nu lambda. It's all good. So I have gamma mu, gamma nu, gamma lambda, right? Three vertices. I have this propagator, ISF, this propagator, K2 minus P, right? This is K2 minus P. This is the fermion propagator, K1 plus P, right? In my notation. Oh, no, sorry. I think the notation was that I'm using is this way. Yeah. Yeah, I think if I'm using it. No, that's good. That's good. Okay, good. Good. All right. This is good. This is the notation I'm using. All right. Then this is the propagator of the photon, right? This is the photon propagator. Now, first thing, we do power counting to see how does this diagram diverge in the UV. If we're in 4 dimensions, I've already written it in dimensional regularization because I know it's QED. But let's just see what it would have what is the form of divergences. This integral will diverge like lambda 4 in 3 plus 1 dimensions. This is a fermion propagator, so it's 1 over lambda. This is another fermion propagator, 1 over lambda. This is a photon propagator, 1 over lambda squared. So the whole thing will have a log divergence. Good? All right. Just by staring at this equation, I won't explain how, but I invite you guys to think about it. Just by staring at this equation, you could see that the log divergent term is independent of K1, K2. I'll leave that for you guys. Here's the expression for the log divergent term. If you can't see this, just expand it, do the like brute force expansion, and you will discover that this is a divergent term. Minus IE squared, this is just the external dimensionally regularized integral outside. 1 over P squared minus M squared, right? This has to do with the fact that I have, how do I want to say this actually? Well, yeah. So this is coming from these two terms, right? At the cost of introducing a P slash up here, right? And then this 1 over P squared comes from this propagator. This is the most divergent term that I have to deal with. You use your Clifford algebra, you know, these rules that you guys have learned, right? To repackage this integral in the following form. This is the external coefficients. You take out some dimension dependent parameter like this, and you write it as the following integral over dp of 1 over P squared minus M squared squared. So you just have to simplify these expressions to see how it works, right? Basically, the point is that they have gamma mu, gamma nu contracted. You have to figure out what that thing is, right? The rest you just factor out this gamma mu. All right, so this integral you can do as well, and you do it using all the tricks that you have learned so far, and this is the expression you find. Surprisingly, you find that the divergent term is absent. So what is going on? This result is gauge dependent. In fact, if you have used this arc-C gauge, in which the propagator of the photon has this eta mu nu, so it would be 1 over p squared eta mu nu minus c minus 1, no, plus c minus 1, p mu p nu over p squared. This is called the arc-C gauge. If you use this gauge, then you find an expression which will depend on gamma, on C. You'll see that in a second. So how do you motivate this arc-C gauge? In Lorentz gauge, what we did was we set the divergence of A mu equals 0, the space-time divergence. Del mu of A mu was 0. Right? This was to ensure that everything is, actually, let me not over-explain. Now, you could add to your Lagrangian, the Lagrangian you start with, the following term, minus del mu A mu squared over C, over Z. And if you added this term and do your variation principle, your path integral, and you obtain your propagator, you find that the propagator ends up with the following form. It ends up with minus 1 over C here. C equals 0 is the Lorentz gauge. Can you guys actually see why, if I stick this in the path integral, C equals 0 is the Lorentz gauge? So what's the job of this term? So I have an integral over S of A mu. I'm adding to it minus del mu A mu squared over C. What's the job of this term? It's a weight term that suppresses terms that have very small del mu A mu. Sorry, the other, which way? Which suppresses large del mu A mu. Right? So if you take C to go into 0, it suppresses everything, and the only thing you're left with is the gauge condition del mu A mu equals 0. Right? So that's the physics of it. It's a trick inside the path integral, right? That's the arc-C gauge. So we haven't discussed this, but this is actually a trick that we absolutely need to use in quantization. We don't have to use it, but it's a very convenient trick that we use for quantization of non-abelian gauge theories. Is this gauge clear, the physics of this, what we're doing? We're just putting this weight function, and it just weighs different field configurations different. And
sorry, do we add to the Lagrangian that term or the action that term?
Yeah, we added to the Lagrangian density. So you have to integrate over this. Sorry, I think there's a space-time integral. Right? Is it good? Yeah. All right. Okay, so if you now redo the calculation they just did for the vertex correction, this arc-C gauge, you learn that there's a divergent term in MS bar and the minimal subtraction bar scheme. You learn that there is this term, which is which diverges, right? So there's a log divergence, but it's gauge dependent. All right, so that was just jumping ahead to telling you what the divergent term is. Now, in the remaining time we have actually, okay, how are we gonna do this? In the remaining time, let's just get our hands dirty with this integral. And we won't be able to finish the discussion today, but we're gonna get it up to a point that next lecture, we're gonna finish the next lecture. So what are we dealing with? There's this minus IE squared. Actually, is this I cube? I think it's I e. Wait. Anyway, sorry. Blah, blah, blah. Yeah. We have this minus I squared mu to this power integral over P, right? And this is the full expression that we have to deal with in arc-C gauge. This is the photon propagator. This factor is the propagator of one of the fermions, and the other one is the propagator of the other. Sorry, I think, let me rearrange these so that it's easier to see. So this is the photon propagator in arc-C gauge, right? Unfortunately, yeah, let me change these two as well. So this is one fermion propagator, and then this is the other fermion propagator. Good. Now you see that you have three parameters downstairs. So the rule for Feynman parameters is pretty easy. You look at the denominator, you look at how many factors squared you have, right? You have three of them. So you have to write down a Feynman parameter integral for 1 over ABC. You write this expression. There is an integral of this form. And then this is one step, right? In the next step, we used to define this L mu. Now you define the L mu in the following way. This is your change of variable. Pushing this through, let's for now set C equal 1 for convenience. I'll come back to this in the next lecture. You massage it into a following integral. I've also yeah, no, I have not changed the order of the integrals yet. So I write as an integral and dimensional regularization over L, X, Y, Z integrals, this expression, L squared minus Q. I've written it like, I've defined L this way so that the denominator is L squared minus delta. That's what you always want, right? And then this is the numerator. We're going to massage the numerator. There are a whole set of tricks. I'm just going to mention a few of them that are being used here. We know that this expression we wrote down was the amputated diagram, which means that it has to be sandwiched with these external legs, right? These external particle wave functions. In these setups, we could use identities of this form, right? The fact that the external legs are on shell to simplify our expressions and turn it into a form of this form. So I leave you guys as for you guys to work out the details of how I went from this expression to this expression. It's not that complicated, but you just have to get your hands dirty with Dirac algebra. So now the point is you have an integral. Now that you got, the reason you write it this way is that you have an integral over X, Y, Z. You notice that X going to Y is a symmetry. Switching X and Y is a symmetry. This term is asymmetric, and the integration range of X, Y is symmetric. Therefore, this term goes away. The reason we do these manipulations is that because we want to show cancellations, right? So we use that to cancel this term. We're left with these two terms. Then, I don't know if you guys remember the Gordon identity, but Gordon identity was something that we used for fermions. We wrote this down for fermions. It was one of your homework or something, homework problem. I think I even mentioned it in class as well. We use the Gordon identity to massage it into this form. Do you guys remember what this sigma was? Sigma mu in Dirac algebra. It was the anti-commutator of Dirac matrices. Anyway, so let me just say, stop here because I don't want to overwhelm you guys with the algebra. We're going to continue this discussion in the next lecture. But let me summarize what we did today. We said, so actually, we'll summarize our discussion of loop diagrams, loop divergences in QED so far. There are three diagrams. One of them was a propagator photon that we call vacuum polarization, right? We calculated that. We showed that in dimensional regularization, there's only a log divergence, right? And then, yeah, that was basically it. We saw that there was a log divergence. Then there was another, and then we use a whole set of tricks. Those tricks we've been using them repeatedly over and over again, right? The second diagram was the correction to the propagator of the fermion. We saw today that we could extract out the correction of the mass of the fermion, right? And the correction of the residue of the pole, right? Which was the overall wave function normalization, the overall function that was sitting in front of the 2-point function, right? And we calculate both of them. That was for the fermion self-energy. Finally comes a vertex. The vertex is the last one, and it's more complicated, right? So we use a whole bunch of tricks. As before, we introduce Fermion parameters. We use these this change of variables, and we're going to use analytic continuation in the next lecture to massage this and get out of it a few lessons. So first thing, I just commented on this earlier. The divergence is still log divergence, right? So it's good. The UV divergence is log divergence. In the next lecture, we're going to discover that this has some sort of an infrared divergence. Now, that has a different origin, physical origin, and that's where we're going to spend the next lecture discussing. All right. Any questions? Just to make sure that you guys are not lost at what we're doing. In the past few lectures, we have been discussing one loop corrections to QED, right? As a simple theory, physically relevant theory, and these methods could and should be applied to any quantum field theory. We're going through all the steps that are required, right? QED is a good example because it has all the subtleties regarding gauge invariance, right? We said that now your theory might have gauge invariance or might have symmetries, right? Global symmetries. If it has global symmetries, I commented on the fact that there are other subtleties, right? The same way that in gauge theory, you had to make sure that gauge invariance the regulator respects gauge invariance. If you have global symmetries, you have to make sure your regulator respects global invariance. If you can never find such regulators, that's the issue of anomalies, right? So that's the story of anomalies in quantum field theory. So there are all sorts of lessons in quantum field theory that have been discovered case by case by going through examples, right? So that's what we're doing. We're discussing them in examples, and in particular, the physically relevant theories. As a matter of fact, the perturbation theory that we're discussing right now, most of this could be instantly generalized to non-abelian gauge theories, which is standard model. All the particles we've ever discovered is going to be SU3 cross SU2 cross U1 gauge theory, right? Plus a bunch of fermions. That's it. This is standard model particle physics. So at one loop, I'm already telling you guys how to make sense of standard model at one loop. Now that has to be done a little bit more systematically, and we're going to discuss that in part 2 of the course. Any questions?
A question.
All right. Yeah.
1 second. One question.